Okay, so say we've found a critical point for a surface. How do we know for sure that the critical point represents a min or a max? When would it be neither? The second partials test allows us to know that information. To use this test, we're going to have to find several second partials. Let's try the test on the saddle function z equals x squared minus y squared. This is a function which we'll find has a horizontal tangent plane at the origin. However, we can see that whereas the values along the x-axis here go up, it looks like values along the y-axis go down. And that's the issue here. We've got positive z's to the right and left along the x-axis, but we have negative z's up and down along the y-axis. So let's go through all the steps here. First of all, I'm going to find the partials, the first partials, that is. The first partials are 2x and negative 2y. Alright, so setting them equal to 0, we would reveal that there is a horizontal tangent plane at 0, 0. It's a critical point. Now we need to use the second partials test in order to decide whether it's a min or a max or a saddle point. Alright, to do that I'll move over. The formula we're going to need is this one right here. Now we had this so far. Alright, so just to use the other notation here, I'll do fx equals 2x and fy equals negative 2y. Let's find fxx. It's a second partial derivative, the partial derivative of 2x. It's going to be 2. And let's find fyy. That'll be negative 2. We also need the mixed partial fxy. And if you recall, you want to take the partial derivative of 2x with respect to y, and that would actually be a 0. Now, in order to do the test, we need to calculate this quantity d, which is a quantity made up of evaluating partial derivatives. So d is going to be fxx at the point 0, 0. I have fxx at the critical point in question, fyy at that critical point in question. And then we have to subtract the mixed partial fxy evaluated at the critical point in question. And we have to square that last part as part of the formula. So luckily this is an easy one where our second partials are actually all just constant. So it won't matter what x and y we're actually plugging in here. All we have to do is multiply the fxx times the fyy and subtract the fxy. So we'll put a 2 in here. That's this. And a negative 2 can go here. And then our fxy can go here. We get that d is negative 4. Now we should go back to the guide here. We discovered a d of negative 4. So if d is greater than 0 and your fxx is greater than 0, then you have a relative min. If d is greater than 0 and fxx is less than 0, then you have a relative max. We actually have the third case here, where our d is less than 0, and therefore we have a saddle point. And you can see why it's called that. The function looks like a saddle.